Hello friends, in this video session I am going to discuss conservation of angular momentum. This is the main concept and important concept from rotational dynamics of 11th class. This is one of the very important concept for JEE mains and JEE advanced all competitive exams after 12th class. Let me start now. What is angular momentum first? Angular momentum is the perpendicular distance multiplied by the linear momentum. Simply you can write as L bar is equal to, you can write R bar cross P bar. This is the definition of angular momentum. It's a linear momentum multiplied by perpendicular distance. Let us suppose a particle moving in a circular path. Particle moving in a circular path about its center, which is at a distance r from the center, circle of radius r. This particle of mass m, it's moving with an angular velocity omega about the center, and it will have a linear velocity v. So here, with respect to the center of the circle, angular momentum can be written as L is equal to linear momentum m into v and perpendicular distance from the center to the r fixed point or about the point which it is rotating to that particle is the r. So you can write here v equal to r omega into r. So finally you can write as mr square into omega. What is m into r square? M into r square is moment of inertia into omega. So angular momentum can be written as L is equal to I omega. This is the angular momentum of a point mass. How to write an angular momentum of extended mass also? You can write as the same. L is equal to I into omega. I is the moment of inertia of that particular body about that particular axis. Omega is the angular velocity with which it is rotating about that particular axis. That is angular momentum. The relation between angular momentum and the torque. So torque can be written as I into alpha. Alpha is angular acceleration, that can be written as d omega by dt. From these two expressions, torque can be written as I into d omega by dt. So rewrite the term, torque is equal to d by dt of I omega. Already you know that I omega is angular momentum. So the torque can be written as dl by dt. This is the relation between torque and angular momentum. Similar expression in a linear motion, we have written that force is equal to dp by dt. This is the relation between force and linear momentum, and this is the relation between torque and angular momentum. So defined as dl by dt. Torque can be written as rate of change of angular momentum. Now what is law of conservation of angular momentum? Law of conservation of angular momentum. In the absence of external torque, torque can be written as dl by dt. In the absence of external torque, no external torque, then you can write as dl by dt is equal to 0. dl by dt, d by dt, dl by dt is equal to 0. So the change of angular momentum with respect to the time 0, nothing but angular momentum is constant. Angular momentum constant. This is a definition of law of conservation of angular momentum. In the absence of external torque, net angular momentum of the system remains constant. So L is constant, nothing but angular momentum can be written as I omega. I omega is constant, and you can rewrite as I1 omega 1 is equal to I2 omega 2. Then moment of inertia is inversely proportional to angular velocity. So moment of inertia is inversely proportional to angular velocity. Means if the particular object is rotating about a particular axis, if that moment of inertia possible if it is reducible, then automatically its angular velocity will be increased. That is, moment of inertia is inversely proportional to its angular velocity. This is correct only when the external torque is 0. So what is law of conservation of angular momentum? In the absence of external torque, angular momentum of the system remains constant. That L is constant, nothing but I omega is constant. I1 omega 1 is equal to I2 omega 2. Now we'll solve the problem based on this concept. This is the one example before going to solve the problem. See, this is the position 1. So look at this position 1 and this is a position 2. In both the cases, see the sked answer. Here hands stretched out, here hands folded. Here moment of inertia will be more, moment of inertia more. In this case, moment of inertia will be less. How? Moment of inertia depends on mass of the body and mass distribution also. So in a position 1, the mass distribution, it is extended, more moment of inertia. Here mass distribution in a second case is less when compared to the first case. So where the moment of inertia more, there the angular velocity less. Where the moment of inertia is less, there the angular velocity more. So that she can make more number of rotation by folding her hands towards the axis of rotation. You can look at this video also. In this video, see the moment she folded the hands about the axis of rotation, then she can make more number of rotations. One in a stretched position, look at it, stretched position, its angular velocity reduced. This is the one of the best application of law of conservation of angular momentum. If she wants to make more number of rotations, she has to reduce her moment of inertia. That is possible by folding her hands towards the axis of rotation. If she want to reduce the angular velocity, simply she can stretch the hands. So that once the hands stretched out, then moment of inertia will be increased, corresponding angular velocity will be reduced. You can see one more example also. Here the case 1, hand stretched out, so that moment of inertia more, angular velocity less. Here stretched inside towards axis of rotation, moment of inertia less, angular velocity will be more. I can give you one more example also. See, this is a two-star system. When the distances are more, about the axis, about this point, there's rotating, right? When the distances are more, their angular velocity less. When distance more, moment of inertia will be more, angular velocity will be less. When the distance between them is less, moment of inertia will be less, corresponding moment of inertia will be less, so that corresponding angular velocity will be more. And you might have seen same kind of application where this is one of the best example to understand conservation of angular momentum. Let us suppose person diving into the pool from a diving board. So before diving, he will stretch the hands, but mid of the case, see in this case, he folded his body towards the axis of rotation to make more number of rotation. Same here also. See, stretched. Here the position, moment of inertia is less, moment of inertia less, moment of inertia less. So that omega will be more, W will be more, omega, angular velocity will be more. Here slowly stretched out. Then moment of inertia increases and corresponding angular velocity will be reduced. These are the examples, best way to understand conservation of angular momentum. Want to increase the score and to get more clarity on concepts, do watch and subscribe YouTube channel of Time for IITJEE and NEET. Now we'll solve few questions based on the same concept recently asked in JEE Mains and CUT and NEET. Now we'll solve the questions based on law of conservation of angular momentum. A thin circular disk of mass m and radius r is rotating in a horizontal plane about an axis passing through center and perpendicular to its plane with an angular velocity omega. Like this is the disk whose mass is m, whose radius is r, rotating about its own axis with an angular velocity omega. This is the initial situation. If another disk of same dimensions are same, but the mass m by 2 placed gently nothing but without disturbing the system on the first disk coaxially, then the new angular velocity of the system. Initially we have one disk whose mass is m, whose radius is r. On this he placed one more disk of the same dimensions. Dimensions are same, but mass is half of the previous one. Is there any external torque in this? Is there an external torque? No external torque, so that you can conserve the angular momentum. Your moment of inertia will be more in the second case because another disk is placed. So that definitely angular velocity will be less than the previous one. So we can draw now I1 omega 1 is equal to I2 omega 2. This is mr square by 2. This is the moment of inertia of a disk about its own axis. Second time we have disk with mass m. We have a disk of mass m by 2. So 2 into 2 into omega prime. Hope you can understand this. That mathematics mr square by 2 into omega. Now I am taking mr square by 2 is common. So left with 1 plus 1 by 2 omega prime. mr square by 2 gets cancelled. We can write as omega is equal to 3 by 2 times of omega prime. Then omega prime will be 2 omega by 3, which is less than half omega. Which is less than of omega. Only reason is moment of inertia in a second case increased. You know, once moment of inertia increases, corresponding angular velocity decreases. That is what we studied in the conservation of angular momentum. Moving to the second question. See, a thin circular ring of mass m and radius r rotating about axis with an angular velocity omega. Now this is a ring whose mass is m, whose radius is r, rotating about an axis with an angular velocity omega. Two particles having same mass, two particles of mass m, each are attached diametrically opposite points. Okay, here also same mass, this also same mass, and this also same mass. The angular speed of the ring will be, again, no external torque because mg acting down. So those are parallel to the axis of rotation, which cannot produce any kind of torque. Simply you can write again I1 omega 1 is equal to I2 omega 2. Initially we have only ring, so that mr square, that is small r is given in the problem. So I can write mr square into omega. Second, once two masses are attached, we have disk mr square and we have two particles each of mass m and at a distance r from the axis of rotation because placed on the circumference of the ring, right? So how many such particles we have? Two particles into 2 into omega prime. Again mr square into omega. This can be written as 3mr square into omega prime. So mr square gets cancelled. Left with omega prime is omega by 3. Even in this case also angular velocity reduced. Same reason. Why angular velocity reduced? Only reason is moment of inertia increased. Because in the second case you attached some masses. Once the masses attached to the system, ultimately moment of inertia will be reduced. Corresponding moment of inertia will be increased. Corresponding angular velocity will be decreased. Going to the next question now. Third question. A particle of mass 2 kg moving with velocity 10 meter per second hits the rod of length 3 meter of identical mass at one end and rod free to rotate about other end and stick to it. This is perfectly inelastic collision. Calculate the angular velocity of the rod particle system after collision. Let me draw the diagram. This is the rod, can rotate about one end whose mass is 2 kg and length is 3 meter. Another particle of mass m moving with velocity v and colliding the rod at one end and stick to it. This is perfectly inelastic collision. So you can conserve the angular momentum because there is no external torque. Before collision, rod at rest, angular momentum is 0. And particle of mass m moving with velocity v and collides the rod at one end. So from the fixed point or axis of rotation, it is at a distance L. So perpendicular distance is L, MVL. and after the collision they move together. So moment of inertia of a rod is ml square by 3, and particle moment of inertia is m, and perpendicular distance is l square, and both move together with an angular velocity omega. So m and m gets cancelled. V is 10, length is 3, and L square is 3 square by 3 into 3 square, sorry, plus 3 square into omega. This is 30. 3n square gets cancelled, 3. This 3 plus 3 into 3, 9. 9 plus 3 is 12. 12 into omega. So omega can be written as 15.5 radian per second. So option is correct. Like this, we can conserve the angular momentum. This is the one of the important concept for all competitive exam. Thank you.